Okay, my friends, this is going to be a fun day in the shop. And what are we going to have fun talking about? Hubble's law and the expanding universe. Well, I got some little toys here to show you something about light and about the universe and about why Hubble, his law is fine if we actually had a vacuum in space, which we do not. It is saturated with particles. And this is not just my statement. This is the statement by Fermilab. But first of all, let's just go to see how they measure things. The method uses the stars or the galaxies as standard candles. All they're doing is guessing at the luminosity. See, it compares their known intrinsic luminosity. That's not known. There's nothing here that's known. So they say, well, we're taking it, well, we know this, and they're taking their intrinsic luminosity, known from similar well-calibrated nearby objects. They can't calibrate them because all of this light is coming through scads of dust. It said then they observed apparent brightness to yield the distance to each object. The further away the object, the dimmer it appears. Well, if it's coming through denser space, it also appears dimmer. All right, this is a little video from NASA Goddard Space Center here, and it's only a couple minutes long, but just listen to this. They're talking about Hubble, they're talking about space, they're talking about seeing these Einstein rings, and we're going to discuss those as well. So here it goes.
An Einstein ring is a very cool feature of gravitational lensing where a background galaxy gets stretched out into a full ring around the foreground lens. A molten ring is a really interesting case where it's one of the largest galaxies that forms a near-complete Einstein ring. The molten ring, you have a very large cluster of galaxies that has magnified this background galaxy. Einstein's theory of general relativity is really sort of what predicted these Einstein rings in the first place. He created this whole machinery for how gravity is supposed to work. Matter would tell space-time how to curve, and space...
This is what I'm going to show you this is actually happening, and I agree with this. But I don't agree that the Hubble Space Telescope can do anything about distances. They have no idea because space is not consistently homogeneous, first of all, and it's saturated with particles.
Space-time would tell matter how to move, and then as you have light moving through this curved space-time, those equations led to the prediction that this light would almost move on what seems like curved paths and cause the phenomenon of gravitational lensing, which is where this light gets essentially bent and distorted by a foreground lens, like a galaxy cluster, and creates these stretched out images that are magnified of these distant galaxies that we see. It's definitely a bit of an optical illusion, so if you were to take the gravitational lens completely away, then these background galaxies would just look like, you know, the normal everyday galaxies that we see at these distances.
Do you see the dust and the particles that are in space? It's saturated. And the other thing is they don't even talk about this. Where did I show you what that thing is? This thing, I mean, this blows my mind if this is a real picture. And I kind of believe that it is because I understand these glowy spots and these curvy spots, and why they're glowing in the places they are, and how these glows interact with each other, because the white is what pushes. All right, now I think that's probably enough for him, but let's go back.
And it'd be a lot harder to pick apart what's going on in their inner workings. So the gravitational lensing effect, it is kind of like looking, you know, at a funhouse mirror. It makes the background object appear a little bit bigger, a little bit distorted. You know, just like you go to a funhouse and you see, you know, your head looks gigantic, your body looks tiny. It's a similar effect, but we can use it for science as opposed to just, you know, looking at ourselves and saying, oh wow, that's kind of funny.
All right, that's enough. Now let's take a look at my toys here and some of our research we did with the light. And this is the thing that they're talking about here. Look at this thing. Nobody's talking about that. Look at that. And the crazy thing is, I sort of have an idea of what's going on here. You see these little bumps all over, and there's like reddish ones, and then there's darker ones, and reddish and darker and reddish and darker in between. and then there's this blue ring around here, and a little lighter one, and then a real bright one in the center, and these flares coming out. Whew. There's a lot to look at there. And all of this stuff, I look at the brightness. Brightness is the key to everything. Brightness is pushing and shoving of particles. That's it. One particle pushes another one, it glows. Let me show you something right here. This is what happens when light comes through the air. All of the particles that are in the air have to get out of the way, because that light is a particle as well, and it has a magnetic field, and that field pushes the fields that these particles have, pushes them out of the way. So they have to glow a little bit, and this glows a lot, because this is the pusher and these are the shove back. Push to shove, that's what I call it, push to shove. Now, what happens after we start accelerating it? Right here it begins to accelerate, and here is full acceleration. The wave no longer is just this rounded wave. It is now being stretched forward like a jet fighter and shoom, pulled right out of it, because there's a venturi here. Now wait till I show you this. This is just beyond belief. This was done by Rod Warren. And this is where it separates. Actually, black separates from the white. 100% separation. There's not one taste of black in here. I mean, in the white. And I'll show you this really close. This is just stunning. When the latest that he did just blew me off my seat. And I've been doing this for 6-7 years, and seen just about everything except for what I just saw the other day. Absolutely stunning. Now these are the Higgs fields, the same thing that Cern is looking for, only we get them out of light, which is much, much better, because they're finding them, but they're finding them in debris, and they really can't tell where they came from. We're seeing them come from this white light, which is only white, no black with it. And what it normally would be is this right here, black and white. I don't know if you can see that. Whoops, you see those little particles? That's what a photon looks like. And when it hits our venturi, it actually explodes and divides the black from the white, which is what I'm showing you up here. The black never gets through, only the white, and that's called electron showers is the white, and the black becomes sterile muons. And then they rejoin over here. But right in this area here, there is nothing but whiteness. There is no black whatsoever. Now, the latest ones he did, he let some of the black squeak through, and it pushes the white. It's just absolutely amazing. Okay, I probably have shown you, or I will show you, that not protons looking like this. Protons look like this. And when you pile up a whole batch of particles so much that there's such critical mass, what's going to happen is when it finally goes off, they crush everything together and it pops all of the white particles, which are these, first. And they hit the house and burn it. Don't even move it, because they don't weigh anything. I'm going to go through this, I think, extremely deep. It could be a while. This is going to take a while to do. But these are the particles that hit the house, and just burn it. Don't move it. And then comes the black particles, which are the ones that are the fixed particles. They knock the house over. Watch this. Now this is from Atom Central. And the first thing goes off is all the white. You see, nothing moves. That's the white particles have hit the house and burnt it. Now the black particles come, knock everything off, and now it all comes back. That is my evidence that shows that there are two complete sets of particles. The white ones always surround the black ones. Always. That's why the white ones come out first. And I show that in the light experiments as well. You see this? This is nothing more than exactly what I showed with a nuclear explosion. It went off here, and everything is going out. The house is here. It's going to burn up. And then the black comes after the burn and blows the house away. You see the black pushing the white? The white has no mass. Nothing. It hits it and burns it. So the house is here. It's burning, 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 burning. Off it goes into Never Never Land in bits and pieces. And then, because this is continuous, so it's not, this, if it went off once, the stuff would have to come back to where it came from. Okay, my outstanding friends, before I get started, if you got kids, or even for yourself, if you just want to get started into understanding chemistry and all these other things, get one of these kits. They're not expensive. Here you get $15, $19, whatever they are. And this Wild Goose company is the one that, well, that's what this is right here, crash and burn chemistry. And it comes with a little manual, and it tells you how to do everything. It's I got the manual around here somewhere, but anyway, it's a place to get kids started to just examine chemistry and these kind of science things outside of the classroom. Have them start to do things on their own. And here, what we're going to do here is I'm going to show you a bunch of little toys I have here, and we're going to play games. If you got kids and you want them to see any of this stuff, get them and have them check this out. Okay, my friends, this is the one you've been waiting for. Can Cern create some kind of disaster with their collider? And we're going to see what they have to say about it, and I'm going to show you what I have to say about it. Now, this is from Future Space, and it's called Scientists at Cern Just Announced a Discovery That Defies All Logic. Now, let's just listen to what they have to say, and I'm just going to cut to the chase here. Here it goes.
That the LHC is a government plot to control our minds and turn us all into mindless zombies. There are also some who believe that the LHC is up to some seriously sinister stuff. They claim that the particle collisions at the LHC are actually part of a secret government experiment to create a new world order.
I just want to make a statement. I'm bombarded by this kind of stuff all the time. So I'm going to show you that I don't see any possible way that they could create any issue with this collider, no matter how much they could collide. Because I have already shown there's black holes all over the place here.
One where only the elite would be allowed to survive. This apocalyptic theory revolves around the idea of a false vacuum, a theoretical state of space where the energy is not at its lowest possible level. If the LHC were to create a false vacuum, it could trigger a series of catastrophic events that would...
They could create vacuums all day long. A vacuum is no big deal. And there is no vacuum in space. Space is not a vacuum. Space is saturated with particles, and that's part of this whole presentation, because Hubble cannot work as advertised. It just doesn't work. Now, they're talking about CERN, these conspiracy people. They're creating something, they're going to try to destroy it, letting the gates of hell out. Well, I really can't totally dismiss that, but I will show you what my evidence is that supports that. I don't think that they can get these particles apart and doing anything special. I don't know though. But I will show you the evidence about the light research we did, which indicates to me that light, whatever they're doing at CERN, they cannot create anything that's going to create these doomsday scenarios.
Would ultimately lead to the end of everything we know and love. This doomsday scenario may seem like a far-fetched idea, but it is a real concern for some experts. The LHC experiments could potentially create the conditions necessary for a false vacuum to form.
A false vacuum? I don't have any idea what they're talking about. What does it mean, a false vacuum? You can create a vacuum. They've done it in space, and they created black holes. They've already done this. And I was not really involved, but I was on the periphery of it. And I tried to communicate with the Russians about it, because this is when it was done, in space in 2014, 2015, in a vacuum chamber in zero gravity. And the dark matter goes right to the center, creates a black hole.
Leading to the creation of black holes that could swallow entire galaxies. The risks associated with a false vacuum are so profound that they could change everything we know about the universe.
Right now, they know absolutely nothing about the universe. They think it's a vacuum. And everything now is just saturated with dust. Hubble doesn't work. Light slows down. The universe is not expanding necessarily. Light slows down as it comes through all of this dense particles in space. It's insanity to think that it doesn't.
It's like Thanos' snap in the Marvel Cinematic Universe, but instead of half the universe disappearing, the entire universe could collapse into nothingness.
See, this is where it just gets nonsense. Let me show you what light actually happens, or when particles collide, what happens and how they reform back together. And then you decide for yourself if we can get a black hole that's going to swallow everything in the universe. Black holes grow, absolutely, no question whatsoever. But they have to continuously be moving through other particles that are attracted to that darkness. Let me show you. The darkness is what attracts them. That's what a black hole is that's what dark matter is that dipole, and it's actually called a muon neutrino. And I'll show you, there's almost no question whatsoever about this. You see that? That's a representation of what they think a black hole looks like, and I believe they're correct. The dark particles that are excess in the universe will collect amongst themselves and have a bright ring around them. And I will show you that actually happening in space. Because space is, the black hole can go to the center and all the charged particles will surround it. And that's exactly what happened in the vacuum chamber the Russians did. And I corresponded with them about this. This is what they did back in 2015, I think 2014, somewhere around. And they just freaked out because they have a vacuum chamber, which means there's no particles in there, there's no gases, there's no dust, there's nothing in this chamber. Then what they did was they injected these charged particles. So they had particles that had excess charges to them. And they all came in, and they were little tiny dust particles, a micron, tiny, 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 with extra charge, like static electricity. It's static will collect on you because it's got a little tiny charge on it. That's what these are. These particles have a little tiny charge. Well, when they came in, they just surrounded a black, dense center. So what they're doing is trying to be attracted to that. And in space, that would be a round hole. It wouldn't be flat like this, or well, flat-ish. It's still being attracted to the Earth, even though they're in space. They're not in zero gravity. They're in very slight gravity. So all this stuff is also being attracted to space, but it's surrounding the dark hole. That's what a black hole is. And they're everywhere. I mean, there's no reason they can't be just literally everywhere. No reason whatsoever. Because the particles coming off the sun stream off of there in all kinds of different polarities. These are particles just flowing out of. Some of them are just the dark particles. They can separate. Well, you just saw it. Some of them can just be the dark ones. Some of them just be the white ones. And then once they're in space, they can sort of drift around until enough dark ones start to grow, and then they'll start to collect the white ones. But they have to just keep growing and growing and growing and growing. I agree. That's how a black hole grows. Now let's take a look at that a little closer. But don't forget, these particles are leaving, and these three spots here are the concussion zones of the sun spinning this way, going that way through space. There's your poles, your north and south pole, and these can actually reverse. If you were spinning this way with the sun, the north pole would be up there. If you were spinning this way with the sun, the north pole would be up here, would be down here. You would reverse its polarity, and I can prove that because this is no more than a sun spinning in space. The magnets are the particles that are in space, and then the core, the center, the commutator, is the sun. It spins like this, and it will give off electricity. It will give off a positive and negative if it's attached this way. It will give off a negative and a positive if it's attached reversed. So all that means is how it spins. So don't forget, there's black hole particles and there's white particles. These are the white ones. Anytime you see something glowing, it's a white particle. It could be attached to a black one, yes. But they can also be not attached and be extremely white, as you will see right here. Wait a minute, look right here. That black was attached to the white. In certain circumstances, especially coming off the sun and luminous bodies, they're going to be divided. They'll be blacks and whites. They'll come back together very quickly, usually. But once they get into the void of space, they're sort of drifting around by their own. If enough black ones sort of meet up together, because they don't care, they'll be right on top of each other. They attract each other just as much as they attract the white. It looks like to me. The black is the holder of the white. It sucks the white into it. And the reason I say that is because of, first of all, this. The black is sucking the white ones to it. All right? The white ones aren't doing anything other than being attracted to the black. So the black is the attractor. And it'll lay right on top of its own self. The white ones won't. They'll push everybody away from them. So they stay away from each other as much as they can, but they still want to be attracted to this black. And they create black holes. And the more white ones they bump into, the bigger and bigger and bigger the white gets. And usually the whites are with the blacks. But the black, they just may be bumping into the black ones too, and the black ones just gloop, 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 they go right into the center. And I think there's more black ones than there is white ones, because the Earth has gravity. Gravity is the black sucking the white ones down. So if the black is sucking the white ones down, we have to have more black in the core, because the whites just keep coming down, and it will attract everyone down to the ground. That's why everything has to be grounded. Electricity will just go bloop, right into the blackness of our black hole Earth. Now, is the Earth literally have a black hole inside? I can't say it doesn't. Nobody knows what it has inside. They talk about iron core and all this stuff. Pfft, no clue. They have no idea whatsoever what's in our center of our Earth. And I see no reason it can't be a black hole. We just see it happens in space. And all of the matter attracts around it. These are all the things that will glow and bounce back at you. It's all like just stuff like this. I see this and the light bounces back. That's not going to bounce back. You never saw this before. You've never seen the dark matter, because it doesn't bounce back light. The light and the dark are attracted together in the Dirac neutrinos, and the Dirac neutrinos make up everything there is. Where are you, my Diracs? Here you are. These two together, the black and the white, or the white, I mean the black and the white. You know, hey, I've heard it both ways. Now, the Majorna is like, as it's the other side of a photon, where it's not really charged up and not charged up. But this is the one I'm going to show you primarily, is the one that you can see and make sense out of, a lot of sense. And here it is. All right. As a matter of fact, here's the whole shooting match at once. These are the smallest particles I can find at Fermilab. This is Fermilab's stuff, and I have Fermilab's article about it. It's called "What's the Point?" And they call this a solid particle that doesn't change. It's called fixed. This is the point particle, which has really no mass to it, but it can glow and not glow, glow and not glow. Fixed, fixed, glow and not glow, fixed, glow and not glow. This is light, all right? That came out of light, out of well, it came out of this. A red pulsed laser. What does pulsed mean? It keeps shooting fast, like a machine gun, only like way fast. And what happens is that whatever bounces back to this, you can tell the distance it's away. This is what this is. This is always a distance measuring laser. They're cheap. And this is what created this exact particles. All this research was done with this right here. That's it. That's what was done with this. Laser through a single slit venturi, which means it forces the particles to come together through this rounded slit. 2 nails, literally nails. I'm not kidding you. And then picked up with CMOS, because CMOS is what is made to pick up luminosity. All right, and we focused. This makes a focus, just like a nozzle on a hose. And there's the nozzle right there. And coming out of the nozzle is a white spray, which is exactly what Cern and Fermilab have been trying to find. And they found it. They found these particles. But then they think there's other particles that are a little bigger than this that are still elementary particles. No, they're not. That's it. That's it. And two of them back to back is like two little bar magnets. Boom. They hold on to each other and they are light. And when they hit this Venturi, they literally explode. The black separates from the white. Separation is fission. Fission means it separates. The black came away from the white. No question whatsoever. And the white came through as a shower, exactly what Cern and Fermilab are looking for. Electron neutrino turned into electron showers. And the muon just goes off on its own. Now, an electron shower, to me, means that one of them came in and then hit a whole batch more and showered them out of the way, which is exactly what it is. Instead of a single cone, the single ball coming in, it just goes. It's like hitting racks of cue balls and boom, shooting them everywhere. And that's what we have here. Is that an increase in energy? I would say so. Anytime you have an increase in luminosity, which is brightness, you have an increase in energy. Well, what does that mean? That means we may be able to get free energy right there. And I think the people at Cern and Fermilab would agree with that. But the problem is that they don't want to see this research looked into because it destroys their research. They're trying to find the same particles we found. We found them for a couple of $100. They spent a couple of trillion. And they still have this big equipment. They're talking about 2029 we're going to do this, in 2040 we'll be able to do this, in 20,000 we'll be able to. And they have never really done anything that I can find ever. Well, the only thing they've done is say we did this, but they haven't done anything. I mean, literally nothing. For all these trillions of dollars, I can't find anything that they've accomplished whatsoever. Here's what their particle physics shows. They hit head on, boom, and all these particles go flying. The red ones are way out on the outside, so they sort of hang around. But way down deep inside, the blue and the green and the yellow, we work with a single color light, which is the red. Well, red and blue and green, we work with all of them. And here's what happens with ours. Instead of hitting head on, we go through and crush the fields together. They're still crushing together. They're hitting their fields head on. Very hard to do. They usually go this way, this way. They just upgraded all their equipment. After I went to the University of Geneva, now I'm not specifically taking credit for this, but I'm going to tell you what. When I went there, I showed them all this research. This goes back to 2016, I think. And I said, we're focusing our lasers through Venturis, and then we're using CMOS to pick up the luminosity. All right, here's what they're doing. They're not using photons. They're using things like this. Two of them head on, just getting debris. We're using this. And seeing it actually change into different types of neutrinos. It literally, we can see it here. It's a certain type of neutrino. Here it's another one. Here it turns into a photon. Here it explodes. And that's what they say. You buy the ice cream here, it's vanilla. Halfway home, it turns into strawberry. Here it turns into chocolate, and here it's tutti frutti. And they realize that this is exactly, precisely, what these neutrinos do. And I showed you, these are what the electron. This is a muon neutrino, the black one. This is the electron neutrino, the white one. When they came in as a Dirac neutrino, means the two of them together. Dirac neutrino. And then they split. The muon went on its own, sterile muon, they call that. The electron turned into electron shower. So there's no guesses here, and I'm a material scientist. I'm not making this up and saying, oh, there must be this, there must be that, and you do all these. I used to do all this stuff here. I got somewhere I showed some calculations. Well, here, I used to do all this stuff. I did all this nonsense, and this was back in 1970. Well, 68, I was in the Army, And I got started at that time. I serviced Nike Hercules missiles. And then I got really involved in this, and then I found out nobody cared about the reality of the situation. I said, you can't have one big gigantic proton and one tiny little electron. It just doesn't work. They have to be dipoles, and it is. The core is a dipole just like that. Every one of these has a plus and a minus. It's not just a minus or just a plus. It's a plus and a minus. When they come together, when you hit a certain number, which that number happens to be, I believe, 1823. At 1823, they stop shaking and they're stable. Proton becomes basically stable right around 1823. 1824 is an even number, so it doesn't. It says I'm even. I'm even, so I'm neutral. I don't want to give one up to become neutral, and I don't want to take one on to become neutral. 1823 wants to do one or the other. Give one up to go to 1822, or take one on to go to 1824. All right, I hope that made sense to you. Neutral numbers are even numbers. They don't want to give or take. So again, I've done all this stuff. I'm pretty well versed at this. Now, what haven't I? Well, a lot of things I haven't shown you, but what I was showing, I think I've shown you that they're looking at this, and they're talking about this as an Einstein ring. Well, that's fine. Call it anything you want. My feeling is this is the earliest stages of a galaxy forming. And this is nothing more than a huge amount of dust and debris that is starting to accumulate towards the dark matter that's inside this bright matter. This is what I'm interested in. Look at that damn thing. Look at that. That's what intrigues me. They're not even talking about it. Look at these. Look at these little spots. And extreme radiation in the center. Then these blue ones. And they fall right in between the two red ones. And then the red ones out here fall in between two red ones. And that's all push to shove. I do understand why they're in the middle of these two. Because there's fields around this one and there's a field around that one. That one snuggles right into the field in the middle. You understand what I'm saying? There's two particles, one here and one here, that are the same polarity, and one will snuggle right in this little crevice. And that's what these red ones are doing. Now, that almost looks like it could be a carbon atom, or something along that lines. I mean, I don't know. I just don't. It's the things I'm seeing lately, I just am stunned every day. But this means that's just nothing more than a cloud of dust. And this glowing part means that something's pushing back against it. Anytime you have glow, it's push. This is pushing against that. You can see it really. And this is pushing in this area. So you've got push to shove. And they glow a little bit here and they glow a little bit here. And the whole thing glows because it's being pushed. Even I got so many shots I can show you that it makes sense of all of this stuff. And this is, it looks to me like it's sweeping around this way and pushing the arm back this way. I'm not sure, but I believe that's got to be a twisting galaxy or star system or whatever. And this all will eventually start to coalesce and turn into a galaxy like this. Where are my galaxy? Galaxy, where are you? Here you are. All right, as this grows, don't forget, I agree, a black hole would just get bigger and bigger and bigger, but it doesn't snap like this and the whole universe disappears. No. There's a black hole in there, no question about that in my mind. And it's completely coated with all those white particles trying to get at it. And as they try to pull in, it starts to pull all the stuff around it, and it starts to create this spinning motion. And as it does, these arms fold back and crush the particles up against that black hole, and it just keeps getting crusher and crusher and crusher. That's a new word I say, crusher and crusher. And these what they call interference patterns, are nothing more than the dark matter in between the glowy particle. And I'll show you that the glowy part can push the dark matter. You want to see this? And this is in Rod's latest shots. Absolutely floored me. Look at this. In his other ones, coming through here, there was no dark whatsoever, only white. And this was just 100% white. Look at this. He's got dark coming through with the white, but the white is so accelerated and so energetic, it leads the dark. Look at that. Look at that. Isn't that fabulous? That's dark matter. It's part of light. They just never realized it. It's attached to the white particle. And the white particle glows, the black doesn't. The black will just be the same size forever, but it's pushing this, and this is really puffing up. Normally, this would be just, it'd be just a little bit of glow there. But when you're being shoved through everybody else, and they have to push everybody else out of the way, that's when you get this push to shove. And you get a separation pattern coming out, and this is just a pusher. This is just pushing like crazy, that black. And that's because at this Venturi was tuned to allow both particles through, but tight enough that the white was so excited that it was really festering, and the black just squirted it through. All right, because this is the normal Venturi where everything's, it's just nothing but white. Absolute 100% zero blackness getting through on this one. And this reverse concussion is absolutely stunning, how much power in the reverse it does. That's why all these particles are glowing like crazy, because they're just being pushed back against. And this is what light looks like. It spins. All of these are particles. Now, you see this one here glowing in the middle? That's because it's getting interfered with by the other particles. Push to shove. Get out of my way, I'm coming through. Yeah, like hell, get out of you. And they just start glowing. They do not want to be next to each other. The white ones do not like to be next to each other. They hate it. They hate each other with a passion. Now, this is what the particles look like as they actually accelerate and become muons, neutrinos, which would be muon neutrinos and electron neutrinos. Here they are right here. You see the black and the white? All right, well, you got black and white here. Well, how come it's so much different there than it was before? It's the same particle. This is all one picture of the same particle because it's going so fast. One shot, and here it is, and here it is. This is pulses. And there it is, backing up real hard, and then exploding. So these are different neutrinos. You got the black, white, black, which is like the Oreo cookie style, and then you got an Oreo cookie on its side, and then you got your photons, and that's because they're dead in line with the Venturi. Other ones are up in here, same stuff as this. It's just you can't see them. They're not being accelerated. These are, and these are also neutrinos. That's a neutrino. This is late, same thing. Now you got white, black, white. Here you had black, black, white. Black, white, black. Here you got white, black, white. Here you got big, long, pushing back fields that are pushing. This is where you create that reverse EMF field that goes back like just stunningly hard. So anything that's coming at it is going to be excited. That's why these ones, where was it? Hold on. All right, that's why these here are being so excited, because it's reverse. This one's being excited because it's coming forward. These are being excited because this is pushing back from this literally subatomic nuclear explosion. And this back here, if you can see it, is still those reverse EMF lines. You see that? All of those are radiating outward like an atomic bomb blast. And it literally is a subatomic bomb blast. And that's why we can see it and it doesn't destroy our equipment, the CMOS. That's what I told Cern and Fermilab. I said, you got to use CMOS. And you got to focus. And guess what? They shut down and did all that. I'm not kidding you. You see this right here. They shut down to put in more powerful focusing magnets. Before, they were just letting them go by and hoping something hit, and it didn't happen. So they put in these new focusing magnets, and then they also did the CMOS. Exactly what I told them. I said, you got to put CMOS and you got to focus. CMOS detector system developments undergo major upgrade to increase its instantaneous luminosity, so they can see this just like we are. Major upgrade. They shut down for 3 years to do the focusing magnets and this CMOS. And like I say, I sent them all this stuff 7 years ago, 6, 7 years ago, and again, I went to University of Geneva online, Switzerland there, and I showed them all of our stuff, and they were quite impressed. They said, wow, how'd you do that? And I said, here's what we did. We focused, and we used CMOS, and, it was, at first it was very contentious, and they were really, no, you can't, that's impossible. I said, no, it isn't impossible. It's exactly what we did, and, explain to me what we're seeing if that's not possible. And finally they said, wow, that's interesting, and we'll follow you on Facebook. I said, okay. I'm not kidding. So anyway, this is pretty serious stuff. What did I show you? Well, here's the green. Green does the same thing, but only it's much more powerful. You see these fields? Here's the black is all going this direction, and the white is coming this direction, but the black and the white is together here. You see it? Over this side, there's no black at all. So this is like an offset. Something like offset like this. No, offset like this. And the light's coming through, it's banging off of this side and shooting out that way. And some of it's coming this way. It's tuning the Venturi. And I'm telling you, Rod spent a long time. I did the same thing. He discovered this. Here's how this all came down. Rod Warren in Australia discovered that if he put light through a single slit made out of 2 finishing nails, and I'm not kidding you, this is it, right here and this. I bought the same equipment he had. When I said to him, what'd you do? I said, how did you do this? And he said, well, I got a Bosch, this exact one, this GLM 15, only he has a metric one, and this Samsung Galaxy S3 phone. So I said, well, I'll get the same stuff. I'll do the same thing. This can't be hard if that's all you're doing, shooting the light through there. Well, it's harder than you think. I spent hours and hours and hours trying to do what he was doing. I get a little this, a little that, but finally I said, let Rod handle it. And he did, and he stuck with this for years, and he's still doing it a little bit, but we haven't had any real correspondence lately, so I don't know really about that. But anyway, this is all his work. I'm not taking credit for any of this. I do the atomic stuff. He had no idea about the atomic stuff. He just stumbled across this and was posting these crazy pictures, and everybody's thinking, wow, what's going on? These are cool, but I mean, look at this. Look at that. He's got his Venturi set up in here, and it's coming through, crushing the fields together. These are the particles forcing themselves together. Here you got your high radiation, which is all your white ones are smashing into each other, and out coming out the other side, they're still spinning, because light spins. This is the other thing. They don't notice particles. They don't understand the wave duality. They don't understand that the observer effect is what they put in there was to observe. They put in equipment to sense these waves, and when they did, they destroyed the waves. So they say every time we look at it, it changes. Well, yeah, because you're putting fields in there. You can't. Luminosity coming out is what you sense with CMOS, and that's all this is CMOS. It means complementary metal oxide silicates. They're different types of transition metals in there, thin filmed, and they pick up all of these particles. But they pick them up. They don't interfere with them. They just see them coming, boop, they light up. They turn the pixels on. So don't forget, this is their Higgs from just smashing things to bits and digging through the trash to find things, really, literally. This is ours. All right, coming through. This is coming right at us. Here, there's nothing. There's absolutely nothing but these white spritzes. See these white little jobbers? And here, it's starting to interact again with the dark particles and turn into Higgs fields. And this was done by somebody else. But I think this is exactly what we are looking at, is the Higgs fields coming at us and the dark particles starting to interact back again with the white particles. Back here, you don't have any dark ones. Every now and then you hit a dark one will reattach down in the wells. These are the forward particles coming right at us. And look at these little... I mean, this is just stunning stuff, man. Look at this. And everything is, they're pushing to shoving. They're stay away from me, I'll stay away from you. Stay away from me, I'll stay away from you. So they make these rings, and then all of a sudden, bam, they hit into reality again, the dark matter. This is coming out of the Venturi. That's what I think it is. Now, I didn't do this, and I think this might have been done at Cornell. We tried to contact the people, but never got any response. I don't know where this was done. I don't think it's Cornell, because I have no idea. I can't remember now. But anyway, this is what happens with our white showers. That's just 100% white shower coming in here. And then all of a sudden you see these. The only time you see these is when the black reattaches with the white. That's what causes these. And they come in little bumps. You can actually see the little bumps. Let me see if I can find one. Higgs on steroids here. No, this one here. You see these? That's the actual particle in the center, and that's the actual particle at the tip. Now this is a really cool one, because they're all coming through red. And it comes through all the white showers, and now the black ones are starting to attach. You see all they just start spinning. These are being pinched, this white blue one, which it was red. It's being pushed and elongated. You see it? It's adding power to it, and then turn it blue. So the color is really it tells you how fast the particle's going, how much impact value it has. And we can show you, or I can show you right now, the green is much more impactful than the red. The red and the green are coming through at the same time. The green is just pushed out of the way, and the red impacts into the green's wake, and then goes dark, and then hits again. So it's a push to shove here, and then it starts a whole new push to shove in here, and then these are impacted again. These are the showers from these particles. It's really beyond belief. And what else? Like I say, with this very, very minimal equipment, we're seeing the particles that the Fermilab and Cern wanted to see. And they do. They see them this way here. And they know that's a photon, I believe. And they see these two together like this every now and then, just only two of them, just like this. And they call that a gluon. And then they also see the muon neutrino, electron neutrino. That's what they see as the smallest particles that exist. But at that point, they think there's more particles that are elementary particles, but are not like this. They're just bigger than that, but they're still elementary particles. No, those particles that are bigger than this consist of these particles. They're just more and more and more of them added together. Instead of just seeing the 4 of them in light, they may see 6 or 8 or 10, and they call it the zoo, and it is. We started with light. We started with the smallest particles there is, so we have no garbage to dig through. They're digging through a whole pile of trash, and they see these separated every now and then. They see them glued together every now and then. They see them like this every now and then. They see them with 8 or 10 or 12 or 16 of them, whatever. And they see them glowing, getting more energetic and less energetic, just like I showed you. The muon neutrinos adding and losing power. And the green does it just exactly as the red does. You see the green here? Here's a green particle. That's the green photon, exactly identical to the red, only it's green. It's much more powerful. And here it is in its neutrino phases. It's coming along, and there's this photon, and here it's going to spin any second, because the one that leads charges up, and then it flips, and then the one that's discharged comes in, just like I showed you on the red, or maybe I didn't show you, but I will. Here it is right here. All right, it's coming in, and the top one is going to get charged up. Okay, the top one is going to get charged up, and then it's going to flip to the back, and the bottom one comes to the front. You see it? How it's upside down? This one here, and now it's upside down here. That's called upspin and downspin. And that happens, oh, I got something to show it easily. Hold on one second. All right, here it is right here. These are the photons coming in. See the little particles? Those are in the gases in the air and whatever it is. And they are in the way of this particle. So as it comes forward, this one here starts getting charged up because push to shove causes light and energy. Anytime you push and shove something, you cause light, heat, and energy. And that's exactly what you have here. This will get to a point where it fills up its whole space, and then it'll go bloop, and that one will swing to the front. And then that one start to charge up. See how it's discharged now? There's no impact to this. This is the one that's impacting getting charged. And this is what it looks like, just in a black and white. You can see how this is more charged, which is this one, and this one's diminished. And this was done by another one, Fabien Brulé, did some of the light work on this, you know, looking at the energy values and so forth. Rod is the one that did the pictures. Now here's one here. Look at this. This is light spinning. This is what it is. And all that is this same laser right here, going through the slit, and this is on the back wall, and it spins just like a drill bit. You see that? That's just like a drill bit. Zzz. Now when they come through the venturi, all of these little bars here are division lines. Stay away from me, I'll stay away from you. Stay away from me. So you're coming through here, zzz, zzz. Some go this way, some come under and go that way. But no matter which way they go, the whites do not want to be next to each other. You see them? They're saying, get away, get away, get away. Here, there's nothing they can do. They cannot get away from each other. That's the spot we see as the white spot. Nothing can be done there. They cannot get away from each other. That's why they fester up in that glowy, insane whiteness. But that's the way light spins. That's a single slit. There's no flappy wave, this and that. Coming out of the slit is where you end up with your interference patterns. Well, these are all interference patterns too. Every one of these is an interference pattern between a glowy one and a not glowy one. All right. Anytime you have a black between the glowy parts, that's what they would always consider interference pattern. So these are interference patterns here, you see? This has just come through the venturi. They were brilliant white, and then they start to slow down as they impact with the rest of the world, and then you can still see them spinning as particles, but they're sort of taking on their own path and staying away from each other. That's just the way it works. They do not want to be together. They do not want to be together. Well, you can see it right there. They're coming out of here. Here, there's nothing they can do. Absolutely nothing they can do. Can't get apart. Can't get it. But here, bam, right there, they start to take on the dark matter. They still stay away from each other as best they can. The middle takes on more of a confluence because they're smashing into each other hardest through the center. And that's where you get your real mess. These take on the stripes. So there's your interference patterns. I hope this is making sense to you. I don't know much more I can show you. The blue is the same as all the rest of them, and the blue comes through really fast. You can't even tell that's got two particles, but out here you can just barely make out that there's two whites there. It's spinning. That's what light does. It spins like crazy, and the blue is really hot. And this is blue through, where is it? Through glass. And you see the interference patterns? Boom, 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 boom. It slows down. Just like the redshift coming towards us through space. Space is nothing more than particles too. This is blue, and you know we're seeing it slow down. It's very, very hot. These whoop. Now the red, you see one here and one out here and one out here and one out here. The green, you see 1, 2, 3, 4, 10. But here, you zoom, that baby's rocking. Blue is hot, hot, hot. And oh, what else? Oh, these here. This is interesting. This is space. These are the magnetic fields. And you see again. Push to shove, push to shove, push to shove, and it's pushing. Finally, as they get way out here, and that's what you got out here. That's the field surrounding, spinning through space. This is the moon. It doesn't spin. It doesn't spin. You always see the same side as the moon. It is impacting, turning blue on that. We can see a blue shift because it's impacting going this way. It has to be. Crushing the fields, and we see the blue shift. But we don't see any field surrounding it. This field is from another, whatever it is behind it. There's a planet back there behind this, which is feeding out this field. And he had some, this is Dylan. It's Rod's nephew. He had some other ones that were stunning. Here's one here, look at this. That's a dipole. And that's a planet. I think it could be Venus. Because it's got two fields. I've never seen anything like this. You see this field here? Quite obvious. Well, guess what? There's another field right here coming out of this field. See this one? You see it? There's two fields. Now, Venus could well do this because it's going around the sun in this direction. And it's supposed to spin like this direction as it goes around the sun. But it's spinning this direction as it goes around the sun. So not only has it got the field because it's going around the sun, which is one of the fields, because you're moving this way, it's got another field because it's going backwards. None of the other planets have a backward spin like that. You can't see. That's the only thing I can take for this. And I don't know if it's right or not. But how are you going to account for two fields with one planet? And you can see how this is so intense. This is just unbelievably powerful, this dipole. And that's exactly what I found here. Where, this right here, look at this. I believe this, again, is Venus. And I believe these are, instead of having a plus and a minus, or, you know, vice versa, you got two minuses. Or two pluses. I don't know what they are. Two somethings. They're both the same. And the core is where all the interaction is happening. That could be with a reverse spinning particle. It's spinning reversely through the universe as it goes through the correct direction, spinning backwards. That's the only thing I can take from this. And this is another one that came through space. That's Venus. You see this one side is black and this one side is white? That's... And then inside the black there's also a white, and inside the white there's also a black. Yikes. That one there confuses me. This is Earth down here. We got pretty much a white side and a black side. And the white side is basically what gets hit with the radiation of the sun in all this, in our atmosphere and so forth. And this one here, it's the black side that's getting hit by the sun. And the white side is away from the sun. I expect exactly the opposite. The sun is over in this direction, and stuff is coming in this way. And you see how it's blank back here? Right? That's because the Earth is obscuring, I believe. And then again, this is all just guesses. The Earth is obscuring all of the impact of the sun back to here. Now this is not doing that. Now why, I don't know. But this is the dark side, and it looks like this is that Einstein ring wrapping around and then just basically dissipating. Because that's what they were talking about in the first thing, is light can bend around other things that have mass. Now this, I don't know. I'm not seeing the same thing I'm seeing here. This is totally 100% different. I'm seeing this interaction, which is almost like this, only reversed. Is the light coming around and sort of banging it into itself back here of the dark particles? The dark particles are the ones that are going to, I don't know, I really don't know at this point, but all I'm telling you is you're seeing some kind of a field out here that's glowy and some kind of a field back here that's not glowy, and then you're seeing a void space. Now what else happened at this exact time was this particle up here, this thing right here, was coming through space, and it shot something right at Earth. And Earth corresponded by putting back a big field like this, a big round field, just like this, a nice round field, like shot out a magnetic ray to stop this particle from coming. Now, what is the possibilities there? Is it possible that we could actually have sent out something to keep us from getting slapped by a bolt of lightning, basically? Or is it just the fact that they're two energetic sources and they mate in the metal because they're magnetic, basically, and they bring together and they met out here? I don't know. But this goes back to 2021, on December 11th, 2021 at 4:08 in the afternoon. And there is so much that has not been explained and is being overlooked. None of this stuff anybody talks about. This is what things used to be like. You see this? Pluto back then, Pluto now. A black hole then, black hole now. We can actually see these things. Atom back then, atom now. And it's true. I go along with this. Only the dark matter is in the core of everything. All right, and these are nothing more than electrons. I won't go along with this atom now. I have my own interpretation of the atom, but this could be an atom. I don't know. An atom of what? Certainly not hydrogen. So, there's a lot to think about, and you have to look at the details. The details are the critical part. You look at it, it's just like a global warming. They think, it must be carbon. No, it's not carbon. The space is saturated with particles. We're scrubbing through those particles. Our atmosphere, that's basically glued to the Earth, is scrubbing the space particles as we spin through and get ripped through the arm of the Milky Way, and it's 2,000 degrees out here. Why would it be 2,000 degrees? Well, it's because it's scrubbing. Same thing with the sun. 10,000 on the surface. Way out here where it scrubs through space, it's millions of degrees. And you have no excuse for this whatsoever, other than, it must be some kind of fusion, diffusion, refusion, delusion. That's what it is. Because it's not, they have to take into account that space is filled with particles. That's why Hubble doesn't work. It's insane to say we're seeing everything going away because the light is shifting. The light is slowing down. It's not that they're dragging the light open. They're thinking that the space is doing this. The particle, all the planets are going like this, and they're pulling the space, the light with them. So we see the light stretched out. No. As it comes to us, the light just slows down. That's all. It's coming out of there fast. And then we see it down here at a stage. And we say, look how slow that is. That means that planet is going away. No, it's not. Absolutely not. It was here when it started, and the planet's still there, and the light coming to us is banging. Bang, 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 bang. And it just keeps getting slower and slower as it comes down. So it's quite obvious. So we're just destroying the planet thinking we're going to get rid of carbon, everything's going to be fine. No. What we need to do is get free energy. And once again, free energy I don't think is impossible. And the way I say, this is the interaction And this is the device. We need something like this, where that laser puts out that stream, and we force the particles to separate here, which is fission. We get fusion here. This is an absolutely unbelievable amount of energy. When you see luminosity like that, that is energy. There is no other possibility. If that energy coming through here in pulses, this is going bam, 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 bam. These are pulses. Now, we can screw around with the pulses. How many pulses? How is this designed? How is the feed for this? What does the venturi look like? Is it a funnel? Is it a whatever you want? How tight is it? Do we want to let some of the black in with the white? Do we want just let the white in? How far away should we put the receiver? What is the makeup of the receiver? Transition metals, some thin film transition metals, as they call them, perovskites. And we could take that, and all of that white stuff is going to hit those metals, those transition metals, which is nothing more than a solar collector, just like they have on the roofs, only it's not that same material. It's much, much more efficient. And it doesn't have to be made to withstand the elements. It's going to be in a little box. Bam, 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 bam. Just slapping the hell out of these white particles. And they are just explosive. When they get in there, if you can funnel them down through a nice big funnel, through a gate, which is a diode, once it gets on the other side of the gate, nothing they can do. They have to be stored in the battery. That's what charging is all about. Boom, 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 boom. Squirt, 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 squirt. And they just keep getting bigger and bigger and bigger with the voltage. And you can do anything you want with it. You use a little bit of it back here to keep the laser going. They say 200 times more energy you can get by doing this, by separating the muon from the electron neutrino. That's what they say, 207 times. Alright, I had to plan to do all this in one video, show all these different devices and how we did all these particle accelerations, and you know how all of the I was going to do everything, how electric motors work, and DC and AC, and you know how to turn on diodes with laser and all of that stuff. We will do that, just not in this video. It just ran a little too long. So there's a lot to go through, because physics is completely different than they thought. It's just nothing like it. The standard model is completely wrong. It doesn't work. What does work is what I showed you, is dipole flood theory, which is the only thing that exists is these two particles. It's the same two they found at Fermilab. It's the only thing that exists. And they can come apart. And they can go together. And they can go together in all kinds of ways. And when there's 1823 of them, they equal what they always considered was a proton. It just happens to be at 1823, they shake, boop, 1823, they lock in, stable. That's the reality. We'll go into all of this stuff next time. We'll do a bunch of experiments, and I'll show you some other stuff that I've got around here that, you know, maybe do some chemistry, do all kinds of stuff. I like playing. It's just, you know, it's interesting. It's something to do.